The use of 4-inch polyvinyl chloride or PVC conduit for 3 sets of number 3/0 American wire gauge or AWG conductors violates the National Electrical Code or NEC section 350.12. b. For 3 sets of number 3/0 American wire gauge conductors, the minimum conduit size is 5 inches according to Table 1 of Chapter 9 of the NEC. If the uninterruptible power supply or UPS load is unbalanced, it can create harmonic currents that flow in the neutral conductor. Harmonic currents can overheat neutral conductors, even if they are not carrying the full load current. The NEC section 220.22 requires the neutral conductor to be rated for the full phase current if the unbalanced load exceeds 150%. We can assume that the neutral conductor should be rated for the full phase current. Therefore, the neutral conductor should be number 3/0 American wire gauge. The grounding conductor is typically sized at 25% of the phase conductor size according to NEC section 250.122. In this case, the grounding conductor should be number 1/0 American wire gauge. Firstly, there is a code violation for the use of 4-inch PVC conduit for 3 sets of number 3/0 American wire gauge conductors. Secondly, the neutral conductor should be number 3/0 American wire gauge to handle potential harmonic currents from an unbalanced load. Thirdly, the grounding conductor should be number 1/0 American wire gauge. It is recommended to replace the 4-inch PVC conduit with a 5-inch conduit to comply with the NEC. Additionally, the neutral conductor should be upgraded to number 3/0 American wire gauge and the grounding conductor should be upgraded to number 1/0 American wire gauge to ensure proper operation and safety. Let's delve deeper into each of these aspects, providing a more detailed explanation and practical context. Regarding the conduit size violation, NEC section 350.12. This specifically addresses the allowable number of conductors in conduit. Chapter 9, Table 1 provides the dimensions and fill percentages for various conduit types. Overfilling a conduit not only violates code but also makes pulling conductors difficult, increasing the risk of insulation damage and potentially leading to short circuits or ground faults. Using the correct conduit size ensures adequate space for heat dissipation, which is crucial for preventing conductor overheating and premature insulation failure. Considering harmonic currents, these are non-sinusoidal currents that are integer multiples of the fundamental frequency, which is typically 60 Hz in the United States. Unbalanced loads, nonlinear loads such as electronic devices with switching power supplies, and certain types of UPS systems can generate harmonic currents. These currents can cause various problems in electrical systems, including overheating of neutral conductors, transformers, and other equipment, as well as voltage distortion and interference with sensitive electronic devices. The third harmonic, which is 180 Hz, is a common harmonic current that can significantly increase the current in the neutral conductor of a 3-phase system. In a balanced 3-phase system, the neutral current is ideally zero because the phase currents cancel each other out. However, when harmonic currents are present, they do not cancel out in the neutral, leading to higher neutral current than expected. To mitigate the effects of harmonic currents, several measures can be taken, including using oversized neutral conductors, installing harmonic filters, and specifying equipment that generates fewer harmonics. Regarding neutral conductor sizing, NEC section 220.22 provides guidelines for calculating the neutral load. The general rule is that the neutral conductor must be large enough to carry the maximum unbalanced load. However, in certain situations, such as when a significant portion of the load consists of nonlinear loads, the neutral conductor may need to be sized larger than the calculated unbalanced load to account for harmonic currents. The NEC provides specific rules for calculating the neutral load in different types of occupancies, such as dwelling units, commercial buildings, and industrial facilities. It is essential to carefully consider the characteristics of the load when sizing the neutral conductor to ensure that it can safely carry the expected current. Pertaining to the grounding conductor sizing, NEC section 250.122 specifies the minimum size of equipment grounding conductors or EGC. The purpose of the EGC is to provide a low impedance path for fault current to return to the source, which helps to trip the overcurrent protective device, such as a circuit breaker or fuse, and quickly to energize the circuit in the event of a ground fault. The size of the EGC is based on the size of the overcurrent protective device protecting the circuit. The NEC provides tables that specify the minimum size of the EGC for different sizes of overcurrent protective devices. In general, the EGC must be large enough to safely carry the maximum fault current that could occur in the circuit. In addition to sizing the EGC correctly, it is also important to ensure that it is properly installed and connected. The EGC must be securely connected to all metal enclosures and equipment in the circuit to provide a continuous grounding path. Let's elaborate on the recommendation to replace the 4-inch PVC conduit with a 5-inch conduit. This is not just a matter of code compliance, it's about ensuring the long-term reliability and safety of the electrical system. Overcrowded conduits lead to increased heat buildup, which accelerates the degradation of conductor insulation. This can lead to premature failure of the conductors, resulting in costly repairs and potential safety hazards. Furthermore, attempting to pull conductors through an overfilled conduit can damage the insulation, creating weak spots that are prone to failure. Using the correct conduit size provides ample space for the conductors, reducing the risk of insulation damage and allowing for better heat dissipation. When upgrading the neutral conductor to number 3/0 American wire gauge, it's important to consider the ampacity of the conductor and ensure that it is sufficient to carry the maximum expected neutral current, including any harmonic currents. The ampacity of a conductor is the maximum amount of current that it can safely carry without overheating. The NEC provides tables that specify the ampacity of different types of conductors based on their size, insulation type, and installation conditions. It's also crucial to ensure that the neutral conductor is properly terminated at both ends and that all connections are tight and secure. Loose connections can create hotspots that can lead to overheating and potential fire hazards. When operating the grounding conductor to number 1/0 American wire gauge, it's important to consider the fault current carrying capacity of the conductor. The grounding conductor must be able to safely carry the maximum fault current that could occur in the circuit without melting or vaporizing. The NEC provides guidelines for calculating the fault current carrying capacity of grounding conductors. It's also crucial to ensure that the grounding conductor is properly connected to the grounding electrode system, which provides a connection to earth. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal water pipes, that are buried in the earth. A properly installed grounding electrode system helps to stabilize the voltage of the electrical system and provides a low impedance path for fault current to return to the source. Moreover, it's essential to understand the specific requirements for UPS systems, as they often have unique grounding and wiring considerations. UPS systems are designed to provide backup power in the event of a power outage. They typically consist of a battery, an inverter, and a transfer switch. The battery stores electrical energy, the inverter converts the battery's direct current or DC power to alternating current or AC power, and the transfer switch automatically switches the load from the normal power source to the UPS system in the event of a power outage. UPS systems can be classified as either online or offline. Online UPS systems continuously provide power to the load through the inverter, while offline UPS systems only switch to the inverter when the normal power source fails. Online UPS systems provide better power quality and reliability than offline UPS systems, but they are also more expensive. When installing a UPS system, it's important to follow the manufacturer's instructions and all applicable electrical codes. UPS systems typically require dedicated circuits and grounding systems. It's also important to consider the UPS system's power requirements and ensure that the wiring and overcurrent protection are properly sized to handle the load. Finally, regular maintenance is essential for ensuring the proper operation and longevity of a UPS system. This includes checking the battery's condition, cleaning the system's components, and inspecting the wiring and connections. Neglecting maintenance can lead to premature failure of the UPS system and potentially compromise the reliability of the backup power supply. In summary, correctly sizing the conduit, neutral conductor, and grounding conductor are crucial for the safe and reliable operation of a UPS system. It's essential to comply with all applicable electrical codes and follow the manufacturer's instructions. Additionally, regular maintenance is essential for ensuring the long-term performance of the system.